A combination of conductors. Now here write subheading combination of conductors. Combination of conductors. Combination of conductors. Now in this first one, series combination. Series combination. Series combination. Now in series combination, now let them to say the area will be same. I'm taking 2 or 3 infinite like this. So I can split now. I'm taking n number of conductors in series. This is one conductor, this is another conductor, this is another conductor, and right. So with dash, right. Now the conductivity of this one is K1, K2, K3, lastly Kn, and lengths are L1, L2, L3, as Ln. So area of cross section is same for all. Now as I am going to apply heat, if I apply heat, what is going to happen? So heat is going to be transferred from this one to the quantity of heat applied. Now these are T, the time of flow of heat. T stands for time of flow of heat. Now then each and everywhere temperature goes on T1, theta1, theta2, theta3. This is I can say theta1, theta2, theta3 and theta4, lastly theta n. Okay, so like this then you have to this one. So in series combination, so what are the thermal conductivities? Coefficient of thermal conductivities we have to take. Now in this below right, heat current is here. Heat current is same is the same in all conductors. In all conductors. In all conductors. In all conductors. Now that means what? Q by T, the rate of heat flow is the same. That is equal to, you say H1, that is equal to H2, that is equal to dash Hn. All are equal. Rate of heat flow is same, or heat current is same. So rate of heat flow is same. Now what is the value of this one? Now we can able to compare with one. H1 place, that is K1A into theta 1 minus theta 2 into time t divided by L1 is equal to K2 area present same theta 2 minus theta 3 into time of flow t divided by L2 divided by L2, and that is equal to dash same thing Kn A theta, that is what we call to say n minus 1 minus theta n minus theta n minus theta n into t divided by Ln. Okay, so areas are same. So areas are same, time is same. We can cancel it. So this is also cancelling. Now finally what you got it is, this is the what relation it is. So you got the relation K1 theta 1 minus theta 2 divided by L1, that is equal to K2 into theta 2 minus theta 3 divided by L2, that is equal to that as Kn theta n minus 1 minus theta n divided by Ln. This is the what you got general. Now the equivalent resistance in this one, equivalent resistance, thermal resistance here. So this is a RTH is equal to R1 plus R2 plus R3 plus that as Rn. This is the equivalent resistance in this case. Now for this we know that resistance formula, thermal resistance RTH is equal to 1 by K into L by A. Okay, then I can take RTH total equivalent. This is a L total length and areas of this one. This is a K series. Okay, series. For that I can write it as 1 by Ks into adding all L1 plus L2 plus L3 divided by area, total area of A. So that is equal to 1 by K1 into L1 by A plus 1 by K2 into L2 by A plus that as 1 by Kn into Ln by A. So A's are all area pressure equal in series. Now, so what you are going to get? So L1 plus L2 plus L3 divided by plus that is divided by Ks, that is equal to L1 by K1 plus L2 by K2, L2 by K2 that is Ln by Kn, Ln by Kn. Now I want to find Ks, so therefore K only reciprocate. So by reciprocating, Ks thermal conductivity is in series. Up here all of you copy. Thermal conductivity is in series. Ks is equal to, I am reciprocating. So by reciprocating, so what is going to happen? So this is going to go to up, one is there. Now we'll go to top. Then we are going to get L1 plus L2 plus L3, okay, plus data dash Ln whole divided by, you can write L1 by K1 plus, I am not in general mathematics, only algebra, K2 plus data dash Ln by Kn. Are understanding? So what I am doing, I am taking total, I am reciprocating total. So what you call, this is a totally denominator 1 is there. I will take to up. What is the denominator here? 1 is there. Denominator here is Ks is there because it's summation. So complete denominator, what is, I can say 1. This is this by this. Now if I reciprocate, then it go to up, and this what will happen? 1 go to up. So 1 go to up, and this is in denominator. Then this is in denominator. I am going to send to right side. It is going to multiply. So this is the lengths are multiply. This is the Ks. Okay. Understanding all of you? Understanding. Now, if supposed to be lengths are equal, now I am going to take, when lengths are equal in lengths. So if lengths are equal, we will get it our original, whatever you want to say. If lengths are equal, if what you call to say, if lengths are equal, then so the thermal conductivity in series is given by Ks is equal to all lengths are equal. I can say n into L divided by, okay, L by K1 plus L by K2 plus dash L by Kn. L is a 1, so you can take L common, you can take from all this one. Better. Now L will be cancelled. Now suppose if two conductors of equal length, then Ks thermal conducting series is, what I write? Ks is equal to n is 2 divided by 1 by K1 plus 1 by K2. Now take LCM and reciprocate. Take LCM. So when that is 2, that n value is how much? You can put here is 2. Take LCM and reciprocate. That is K2 plus K1. You will take this K1, K2 LCM. That is 2 into K1, K2 divided by K1 plus K2. So you got, and two conductors of same length, they are connected in series, then their thermal conductivity is, so we know if I give the formula you can enjoy. You are reading formula by hearting. Finally once the question comes, confusion will come. If the lengths are not equal, then what to do? So when the lengths are not equal, what is the thermal distance formula? RTH is equal to R1 plus R2. Okay, what is R? R is equal to 1 by K1 into L1 by A plus 1 by K2 into L2 by A. So here is what is the total? 1 by Ks. Here is L1 plus L2 by A. Then take it as L1 plus L2 by Ks. Areas are same, cancel. L1 by K1 plus L2 by K2. So what to do? You take LCM here. Suppose if the lengths are not equal, suppose what to do? So in this case, then if you know method, then you are easy. So generally, normally students are making to by hearting the formula, then they are going to get a lot of problem facing. So I am going to say if lengths are not equal, if supposed to be if lengths are not equal, then I am taking two lengths only. By taking 2, so equal, that is by taking 2. I am taking 2 lengths, taking 2. Then what you are going to get? So 1 by, this is a Ks, so L1 plus L2. So area of fraction cancel, no need to write again. So then L1 by K1 plus L2 by K2. Now take LCM, that is K2L1 plus K1L2 whole divided by K1 into K2. Okay, na sir? So therefore Ks is equal to K1 into K2 into L1 plus L2 divided by this you can take. So I can take K1L2 plus K2L1. So that's all. I have not done anything. Suppose if lengths are equal, what you can say? L1 is equal to L2, that is equal to L, say. Then what happened? This is a L plus L, 2L. So this is L, common take. So that is LL cancel, 2 is there. Then finally you are going to get Ks is equal to, okay, so 2 K1 K2 divided by K1 L2 plus K2 L1. This is the, so if it is not equal, this is a formula. Copy. Now see here, then lengths are equal, L1 is equal to L2 is equal to L, then 2 K1 K2, okay, that L already cancel, this L, therefore K1 plus K2 only, K1 plus K2 only, okay. Now understood? Okay. Now I'll go to next concept for this. Okay, next concept. See here, next concept. Now right here. Now right. That interface temperature of composite bar. Interface temperature of next one most important, interface temperature of composite bar. Interface temperature of composite bar. I am taking two bars. So let them take two bars. Now I am going to divide this one. This is a bar 1, this is a K1, the K2. Here the temperature is theta 1, here the temperature is theta 2. This is the interface temperature theta. So what is the interface temperature theta you want to find? Okay. Now for this what length is L1, L2. Areas are same areas. You can say same area of cross section, no doubt. And time of flow is same also. So time of flow is same. So the rate of heat flow or current flow Q by D in series is same. So that is equal to both are whatever rate of heat flow is there, same rate of heat flow will be there. So that is equal to, I can write K1 A into delta theta, that is theta 1 minus theta, already time is here written, divided by L1 is equal to K2 area of cross section into theta minus theta 2 divided by L2. So areas you cancel, no more doubt. Now from this equation you have to try to find theta. From this you have to find theta. What you do? You do the cross multiplication. Then what I can get? K1 L2 theta 1 minus K1 L2 theta, that is equal to, I am writing here, K2 L1 theta minus what do you call say, K2 L1 theta 2. So I want to theta. Here is minus is that, bring this side. So I can take theta common. So K2 L1 plus K1 L2. Now take this fellow to that side. So now I can, which is a common here. So K1 L2. So no common. Theta 1, theta 2. No problem. I can write as it. No commons are not there. So I can write K1 L2 theta 1 plus K2 L1 theta 2, that is our. So therefore interface temperature theta is equal to, I can write it as, so K1 L1 theta 1 plus K2 L2 theta 2 divided by, to write K2 L1 plus K1 L2. So this is called interface temperature. With respect to thermal conductivity. Look here, this again, the same formula can remodify. Okay. Now theta is equal to, so I can read it as K1 L1, K1 by L1 into theta 1 plus K2 by L2 into theta 2 divided by So I can write K1 by L1 plus K2 by L2. So what you do? Multiply and divide with L1 by L2, numerator denominator. So you get that. So now suppose if L1 is equal to L2, that is equal to L, say, then what is going to happen? Now this all are equal, L1, L2, so L's are equal. Now what was the remaining part will be done. Okay. The same one, another method is there. I want to find the theta, then what to do? So from that, another method, theta 1 minus theta is equal to theta minus theta 2. When thermal conductors are same, then what to do? Then this you can take to this fellow this side, that is theta 1 plus theta 2, that is equal to 2 theta. So therefore theta is equal to by theta 1 plus theta 2 divided by 2, by this also. Okay. Right. Now, okay, good. Now, very nice. Now, go to the parallel combination. Next one is parallel combination. Parallel combination. Right. Parallel combination. Very simple, easy, right? Right. Next, right. Parallel combination. Start. Next, second one is parallel combination. Parallel combination. Parallel combination. So generally, how should be the parallel combination? Lengths are equal, so one upon another are keeping the conductors. This is the conductor 1, this is the area of cross section, and another conductor, this is the area of cross sections, and another conductor inside is there, actually like this, not like this. So I'll say n number of conductors, you can ignore all. So this is the now the area of cross sections are different, okay, but lengths are same, okay sir, lengths are same. So this is the, I can take A1, this is A2, this is A3, this is A4, like this. Now this source of heat, I am applying the heat to the heat application. So length is common length L. Length is equal to common length is, and the thermal conductivities are K1 and what is called K2, K3, K4. These are thermal conductivities. There are thermal conductivities. Okay, sir. Now, in thermal resistance in parallel is given by that equivalent resistance, equivalent resistance. So 1 by RT formula, sorry, 1 by RT, you can say 1 by RT is equal to 1 by R1 plus 1 by R2 plus that is 1 by Rn, 1 by Rn, all of you knows. But here the total, the rate of heat flow Q by T, that is equal to H, is equal to, you can have to add H1 plus H2 plus that Hn. Okay, H1 plus then adding only. So for this I can rewrite that is equal to, so that is equal to, so that is a K, what is called thermal conductivity K, total K is called Kp is equal to areas A1 plus A2 plus dash dash AN into temperature difference. This is a theta 1 and this is the other end is theta 2. Okay, sir. Then I can write theta 1 minus theta 2, theta 1 minus theta 2, theta 1 minus theta 2 into time of flow T divided by length, same length L, that is equal to, now what is the RHS? This is K1 A1 theta 1 minus theta 2 divided by L, lengths are equal, plus K2 A2 K2 A2 K2 A2 theta 1 minus theta 2 divided by L plus that you can write. So which is the common there? So temperature difference is same and the length also same. Okay. Now, so we got K into A1 plus A2 plus dash AN, that is equal to, now I can write it as K1 A1 plus K2 A2 now. So therefore, the thermal conductivity is in parallel, Kp is equal to, then you can write K1 A1 plus K2 A2 whole divided by A1 plus A2 plus dash. So then Kp is equal to, then what I can say, K1 A1 plus K2 A2 dash this one. So K1 plus A2 dash is okay. Now finally what you can say, when what you call Wheelerite. If A1 areas of process are equal, if A1 is equal to A2 is equal to A3, that is equal to that. So AN, that is equal to A. Then what you can do? So thermal conductivity K P is equal to, okay, K1 plus K2 plus K3 plus dash by N. If there are two conductors supposed to be, if two, right, if two conductors of equal areas of area of cross section, areas of cross section, then thermal conductivity parallel Kp is equal to average K1 plus K2 divided by